Everyone, let's make a start with lecture 6. So in lecture 6, we're going to build on what we've done so far, and we're going to see how particles emerge. So I just wanted to recap again, just to make sure you're all on the same page and have the bigger picture in mind. I wanted to recap what we've done. So one of the things we have discussed is this procedure from how to go to a classical to a quantum theory. So I've given you this kind of 5-step recipe that you can follow in order to quantize the theory. So just to remind you, step 1 is when you start with the Lagrange density. So that kind of defines your theory. You then go on and calculate the conjugate momentum, this thing pi. You can construct the Hamiltonian density, this curly h thing, from knowledge of pi, from the time derivative of phi, and the Lagrange density. Then we get to the stage where we make it a quantum theory. So we promote our fields, pi and phi, to operators, and we impose commutation relations between them. So in classical theory, there are no commutation relations. In the quantum theory, we do have them. And then we expand our operators, so pi and phi, in terms of annihilation and creation operators. So these were these A and these A dagger operators. And then finally, when we discussed the Hamiltonian, we saw the importance of this normal ordering step. So this gets rid of the, ambiguity in going from the classical theory to the quantum theory. Okay, so we've been looking at this particular simple theory of the real scalar field. So this is a real field with no interactions. So we just have a kinetic term and a mass term. And so we've been able to work out what the field is. We've been able to work out what the conjugate momentum is, and we've been able to work out what the Hamiltonian is. So the Hamiltonian is just a sum over A dagger A for each momentum mode labeled by P. So we just sum over this infinite number of modes. But most of you would probably describe yourselves as particle physicists, or yeah, probably most of you, and not field physicists. So we spent all of our time talking about fields in a school for particle physicists. So in this lecture, I want to discuss and show you how particles emerge from this field point of view. Okay, so that's the aim of this lecture. So hopefully by the end, you'll see how particles are actually embedded in this field framework that we've been looking at. Okay, so as we discuss how particles are going to emerge, let's start by considering a particular state. So I'm going to consider the state where we have one of these creation operators labeled by P acting on the vacuum state. I should say, in this lecture, I'm probably going to not write the little, so normally I'm careful to write hats. I'm going to be writing so many operators in this lecture that I'll probably drop the hats just to clarify notation. But hopefully it's not clear. If I write AP dagger, I mean the operator, the creation operator. So we want to consider this state. And my claim that I want to get to is that this state represents a particle. Okay, it represents a particle with a definite momentum and a definite energy. And this is how particles will emerge in quantum field theory. Okay, so let's start by considering a particular aspect of this state. So let's think about what the Hamiltonian acting on this state will give us. Okay. So in order to answer this question, I first want to show, well, we need a relation. So we want to show that the commutator of H with P dagger is omega P AP dagger. Okay, so this is something we stated. Well, or at least maybe we did it for the lowering operator, but it was a similar form. We stated this type of relation as an assumption in one of our earlier lectures. But now that we have the representation of the Hamiltonian in terms of raising and lowering operators, we can actually prove this. So let's actually show you how to prove it. It's also the reason I want to go through it is also to give you examples of how to do calculations in this canonical quantization framework where you have to manipulate these commutation relations all the time. Okay, so H A P dagger, well, we know what H is, so H is going to be a sum over momentum mode, so I'm going to label the H states by K. We had omega K, so these are all numbers that I'm going to pull outside of the commutator, so without this square bracket, this is what H would be. So the only bits that matter for the commutator are the operator bit, so the A dagger, AK, and the commutator we then have to evaluate is this piece. Okay? So we just use some of the standard techniques to actually simplify this commutator. So first of all, there's a general relation between commutators that if you have AB with C, kind of split this following way. Okay, so it's a product of a commutator of just two terms. Okay, so in our case, we have AK dagger, AK, AP dagger. Okay, so we're going to have AK dagger, K, AP dagger plus this second term, none. This is where we make use of the commutation relations that we know about. So to remind you, we know that commutators of daggers with two daggers in it are 0, so these things will commute with each other. That's nice because that's going to set this term to be 0. And we need to remember, let's use the same labels we have above. So we have to remember that AK, AP dagger is 2 pi cubed and a delta function d, or delta 3 a minus p. Okay, so we just substitute that in. Okay, we substitute this expression in here, and that gives us that. Well, actually, let's go back to the full Hamiltonian expression. So the expression we have at the top. So we're going to put in this commutator in here. You write down all of the integral stuff and the omega k, and then we can substitute in for this commutator state, which we're saying is just AK dagger with this delta function from this relation. So this is pi cubed delta 3 AK dagger. Okay. The nice thing about this is that we can integrate over the delta function. Okay, so the 2 pi cubes are going to cancel, and we can integrate over the delta function, which will just set k equal to p. So we'll find omega p AP dagger. Okay, so this was precisely the relation we were trying to show. Okay, so we wanted to show that this holds, and we have. Fantastic. It's always the same steps with these commutation relations. If there is some product of terms, you just use some identity. Either you know them or you look them up. Typically what you'll find is some of the commutators vanish, like they did in this case, and then, often delta functions appear to get rid of some of the integrals, as happened in this case. Okay. So what does this relation mean? This relation means following: that H A dagger minus A dagger H is omega A dagger. So this is the relation that we want to use when we go back to the thing we wanted to calculate. Okay, so this is really what we want to calculate, H A P dagger. Back to H A P dagger. So we want to know what this quantity is. So the general strategy when you have things like this is to try and bring the H so that it acts first on the state 0, because by definition H0 equals 0. This is the definition of the vacuum state. So if we can bring H through to the state 0, we'll get a bunch of zeros, so terms will cancel, things will simplify. So we're going to try and do that, and we do that by making use of this relation above, this commutation relation we've just found, because this tells us that H A dagger is, well, omega A dagger plus this piece when we bring it across. Okay, so in other words, this is P, AP dagger plus AP dagger H, all acting on the state 0. So as I said, by definition, H acting on 0 is 0. This is the vacuum state. And at least, I should say, by definition, it happens in this case because we've set this infinite energy term to 0 through this normal ordering process, right? So because of this normal ordering process, this term is 0. So we are simply left with omega P, AP dagger 0. Okay, very straightforward in the end, but let's think about the interpretation. So what this is telling us is that the state AP dagger acting on 0, this is a state, and this Hamiltonian tells us about the energy of the state. The energy eigenvalue is omega P. This is a state with an energy omega P. And just to remind you, the definition of omega P is, well, the square of it is P squared plus M squared. This should be starting to look like something that you would expect for a single particle, because this is the familiar, what do we call it, energy momentum dispersion relation for a single particle of mass m. Okay, so this would be the E squared is P squared plus M squared. Obviously, we're using natural units. We've set C equal to 1. This is E squared is P squared plus M squared. So certainly this bit's the energy because we've just shown it. So the Hamiltonian acting on the state tells us that this is the energy. And this, with the notation we're using, certainly looks like a mass, and the P certainly looks like a momentum. But I guess you could say, well, I'm still not convinced because I don't really know what these things are. Okay, you've defined omega P squared to be P squared plus M squared. And okay, I accept that this is the energy, but for this to be the energy momentum relation, there's one extra thing I want to see, and I want to really see that this is the momentum of the state. So that's something that we can do. Okay, so let's think about how we do that. So to really show that this is the energy momentum relation, let's also work out the momentum. So we haven't discussed the momentum so much. So let me remind you of what it is, or how you can define it. Okay, so classically, we can get our momentum from the 0I component of the energy momentum tensor. Okay. And for this theory that we're working with, this turns out to be d3x I with the derivative of phi with respect to the ith component of the spatial derivative. So if we wanted px, this would be d phi dx. If we wanted py, this would be d phi dy, and so on. Okay, so that's the classical relation. I guess we can say in the quantum theory, well, we know what we have to do. Okay, these fields get promoted up to operators. Let me put the hat on. Let me be a little bit more careful. Put the hats on, so we're not going to have a momentum operator. And the momentum operator should be, I'm going to use this normal ordering symbol. So it should be this expression when our fields are promoted to operators and when we apply normal ordering to it. Sometimes you can use n for normal ordering, or you can use this 2-dot notation. So I didn't, just as with the Hamiltonian, I sort of skipped all of the steps to actually derive how you can express P in terms of the accretion and annihilation operators. I'm going to also postpone it here, so I'll just quote the result. So the result is d3p, 2 pi cubed, and then we have the number that's associated with the momentum. So it's not an operator, it's the number. And then we have this combination of operators, AP dagger AP. Okay, so in other words, it looks a lot like the Hamiltonian relation, but rather than omega appearing, it's P that appears here. So I think correct in thinking that the problem sheet actually asks you to do this calculation. So to go from these, to go from the first line down to the second line. So I'll leave that as a discussion that you can have with your tutors. Okay. But the point is, we now, or well, I've told you what the operator is for the momentum operator. So just as we considered the Hamiltonian acting on this state, which I'm claiming is the one particle state, we can then consider this momentum operator acting on this state that we're interested in. So it was a dagger acting with a 0. So this time, label it with a K. I think before I use P, but because I'm using the P operator, I'm just going to switch the label and have a K, but otherwise everything's the same. So we want to consider this relation. So again, I would like to show that P acting on this state really does give me it really does return, well, that this really is the momentum operator, and it really does return the momentum of the state. So let's go ahead and do that by using the definitions. Okay, so putting in the definition of P first of all. Okay. Except, yeah, I actually do want to use P. Right. PI, and then we'll have A, P, dagger, A, P, and we want to act on the state A, K, dagger, 0. Okay, so the strategy is similar to our Hamiltonian strategy. So we want to bring the things that are going to give 0 when they act on the vacuum state to the right. So in this case, we know that AP acting on the vacuum state is 0, so we want to bring our annihilation operators over to the right-hand side. So we can just use our commutation relations to do that. So we're going to use that AP, AK dagger, AP, 2 pi cubed delta 3 E minus K. Just our familiar commutation relation. So we've got all of these factors as before, and then we're going to have an AP dagger, and it's the final two in our expression above. So in other words, these two that we're going to replace with our relation, with our commutation relation. Okay. We do that, this is the expression that we get. So as I said, by definition, AP, this annihilation operator acting on the state 0, returns 0. So that term is simply going to be 0. And we will get, well, the 2 pi cubed factors are going to cancel. And we can integrate over the delta function with the dp3. Okay, so when we integrate over that delta function with respect to p, it's going to set p equal to k. So we'll get ki a k dagger 0. Okay. So again, it's fairly trivial, right? It's just applying the commutation relations, but let's think about the interpretation. What does it mean? So here we would interpret this state a dagger 0, a single particle state. Okay, and what do we know about this state? Well, we know its momentum is k. Okay, so I've done it for the ith component, but You can do it for the x, y, and z component. Okay, and pick out the full 3 vector of the momentum. So its momentum is going to be k. We applied the Hamiltonian. We know the energy is omega k. This omega k satisfies a squared plus m squared. Okay, so omega k really is the energy, k really is the momentum. We really do recover this single particle energy momentum relationship. So this quantity m really is the mass. Okay, so that's one way of showing that the state satisfies all of the properties that we know that a single particle state should satisfy. So we know about its energy, and we know its momentum, and we know it has to satisfy this relation that's consistent with relativity. Okay, so next I want to briefly introduce some convention that you'll see in most textbooks. Okay, so let's introduce some convention for a momentum eigenstate, for a single particle state. So we've been talking about the state AP Dagger acting on 0. So it's more conventional to label this state as well with the label P, and to put in this factor. Okay, so rather than just having AP Dagger 0, so we've shown that this state, technically have a little line under there, although I haven't been putting them throughout most of it, but that this really is a momentum eigenstate, right? When we acted on this state, we returned the momentum eigenvalue, so it really is a momentum eigenstate. But it's more conventional to put in this factor root 2, and here I'm going to switch from using omega to E, right? Because we've just shown with the Hamiltonian, this omega factor really is the energy. Okay, so omega p and EP really are equivalent, so I can use EP or omega p. So we add in this factor. So why do we do this? Well, this factor root E2P, root 2EP does something important. So it ensures that my normalized, or rather my bracket, consider the ket of the state Q with P, that this is Lorentz invariant. Okay. Let me give you a sort of semi-proof of this. So I'll do the first half of the proof and leave the second half for you to complete in a problem sheet. Okay, so let's consider what QE is. It's going to be root 2EP, 2EQ, and then we're sandwiching these operators between the vacuum states. Okay, and now we want to use our familiar anti-commutation relation. So commutation relation, not anti, but commutation relation. To follow this kind of strategy of bringing my annihilation operator to the right-hand side, so that when it acts in the vacuum state, I get a factor of 0, and that bit just cancels. Okay, so let's do that. Okay, so I'm going to have, rather than this state, I'm going to replace it with this plus this. Okay, so it's 2 pi cubed delta 3 plus AP Dagger AQ. So as promised, when AQ acts on 0, we get 0. So this is going to cancel. And we're simply left with a number, or it's certainly not yet, it isn't a number, between these two states. Okay, so this doesn't change the states. So we're going to have 0 acting on 0, which is normalized to 1. So we simply get 2 EP 2EQ okay, so we simply get this. Okay, and this is again because 0 with 0 is 1. So that's the way we have normalized our states. There's a further simplification we can in fact make here. Okay, so in any expression where we actually would use this. Okay, what this delta function is doing is setting the three components of P equal to the three components of Q. This implies in any expression that P is going to equal Q. So for these states, so these are all single particle states for a particle of mass m. So for all of these states, if P is equal to Q and if the mass is the same, this implies that P squared plus m squared is Q squared plus m squared, or in other words, that EP is equal to EQ. Okay, so this delta function does all of this, which means we can simplify this term a little bit, because in reality, P is going to be the same, sorry, EP is going to be the same as EQ. So this is going to be 2EP 2 pi cubed delta 3 Q minus P. Of course, we could have labeled it with a Q as well, Q and P. EP and EQ are the same, so it doesn't matter. Okay, so we want to show that this product is Lorentz invariant. So we've sort of redefined the problem a little bit. This bracket will be Lorentz invariant so long as the right-hand side is going to be Lorentz invariant. Okay, so now if this EP delta 3 Q minus P it's the same. So after a Lorentz transformation, so my primed quantities here are EP and these are P and Q and EP after a Lorentz transformation. So as long as we find that this holds, okay, so for the Lorentz transform quantity, it takes the same form as the re-transformed version. Then this QP bracket is Lorentz invariant. Okay, so this final step is one that you're going to tackle in a problem sheet. Okay, so this is a problem sheet problem for you to solve to do this final step. So the purpose of the problem sheet problem then is that you can complete this proof and really show that our single particle states, or that it's sensible to define our momentum states with this additional factor so that we get this Lorentz invariant bracket quantity. Okay, so with this new notation that we have, we're now saying that this state P, this is a single particle state, so it describes a particle with a definite energy and a definite momentum. And the momentum's P. Okay, but I think you would still be justified in asking me, well, where's the particle in this state? Okay, so at least the picture I have of the particle, you know, is something that's kind of some finite little thing, right? There's an actual thing that's somehow localized in space, and that's what I take to be a particle. So with this state that I'm claiming is a thing that represents a particle, where is the particle in this state? So here you have to remember that we're dealing with quantum mechanics here. This really is a good particle state, but this is a special state. This is a momentum eigenstate. Okay, so what do we know about momentum eigenstates? Well, with momentum eigenstates, by definition, the momentum is known, and it's known exactly. Okay, so, you know, momentum eigenstates have this very particular property, and because of this fact that we know P exactly, the quantum mechanic uncertainty relations, the Heisenberg uncertainty relation, well, this tells us that because P is known exactly, X is unknown. Okay, so with this particle state, which is a momentum eigenstate, we cannot think of of a particle as some little discrete thing, okay, its position is maximally unknown because we know its momentum precisely. Okay, so this is a particle state, but it's not a confined thing which is localized at some position in space. But if we wanted to, we could construct a thing which really is localized at some position in space, right? So that's going to be what we call a position eigenstate. So for particle physics, most of the time it's more convenient to work, at least in scattering problems anyway, it's more convenient to work with momentum eigenstates. But we can also construct position eigenstates the following way. So the relevant thing we need to consider, so we want to construct a state X. Okay, so let's not worry about the time dependence. Okay, so let's just worry about constructing a state which is going to be at X. So I'll tell you the answer. The answer is that the momentum eigenstate X simply my phi operator acting on the momentum state. So here, as I said, I'm not worrying about the time dependence. So this is a Schrodinger operator. Okay. Quite soon in one of the upcoming lectures, we'll see how to, you can put in the Heisenberg operator if you want, but since here we're considering the case where it's fixed at one point in space-time, the Schrodinger operator is sufficient. Okay, so let's just actually look at what this is by using our expansion of phi in terms of the creation and annihilation operators. Okay, so here we have p dot x. So these are the three vectors because this is in the Schrodinger picture. And we want to act on the state 0. Okay, so by definition, AP on the state 0 is going to be 0. So this term is going to vanish, and we're going to be left with d3p 2 pi cubed to 1 over root 2 omega p e to the minus I p dot x. And then we have the state AP dagger on 0. So this is almost, in fact, this momentum eigenstate that we were just talking about up here. We can, in fact, make it into momentum eigenstate by, we need this extra factor 2 times the energy. So here I'm writing the energy as omega, but we could use E. And we also divide by it. So I'm just adding in the number 1, AP dagger on 0. So in other words, let's simplify this a little bit. We've got the d3p 2 pi cubed. Let's bring together the 1 over the square root of 2 omega p factors over 2 omega p e to the minus I p dot x. And then this combination of root 2 omega p AP dagger 0 is simply this momentum state that we had already introduced. Okay, so what we find with this momentum, what we find with this position eigenstate is now X is known completely. So our momentum, in fact, in this case is completely unknown. And we can see that from the expression above, from the fact that we have to sum over all possible momentum eigenstates. Okay, so here we're summing over all of them. Okay, and this is what this integral is doing. So you can use either of these pictures. So you can use the picture where we have a momentum eigenstate, but then the position is unknown. Or you can use it as a position eigenstate. Did I say that properly? You can use a momentum eigenstate, its position is unknown. Or you can use a position eigenstate, but then its momentum is unknown. So we can express our position eigenstate in terms of momentum eigenstates, and you see you get this infinite, you have to sum over all infinite momentum states. This is exactly equivalent to what happens in normal quantum mechanics, in fact. Okay, so you can express, if you wanted to go and check a quantum mechanics book, you can express your position eigenstates as a sum over momentum eigenstates, and you'll get the same factor. You'll get this e to the ip dot x factor. So you might normalize your states in a different way, so you might not get this 1 over 2 omega p factor, but everything else should look the same as in standard quantum mechanics. Okay, we've spent all of our time so far thinking about one particle states. A universe with a single particle perhaps isn't the most interesting. So let's generalize our formalism and show that we can also describe more than one particle. In particular, I want to go from 1 to 2. Then I'll leave it to you if you want to go for more than 2 particles. Okay, so if our state AP1 dagger 0 was a 1 particle state, in other words, if this iteration operator is creating 1 particle, you might expect, or you might guess, that the state AP1 dagger AP2 dagger 0 might be a 2 particle state, because with a P2 dagger, I'm creating a state with momentum P2, and with the P1 dagger, I'm creating a state with a P1. So let's show that that is the case, and let's show how you can show that it's reasonable for that to be the case. So we're going to do the same thing as we did before. We're going to first act with the Hamiltonian, but now act on the state AP1, AP2 daggers. Okay, and we're going to use the same strategies that we've been using before. So namely, we want to bring the Hamiltonian operator to the right so that it's closest to the vacuum state, because H acting on the vacuum is 0. So we're going to use commutation relations to do that. So in this instance, the commutation relation we want is H with a dagger. Just to remind you, H dagger, the full expression, so we have it. So we have the H AP dagger minus AP dagger H is omega P AP dagger. This is what we want to use. Okay. So let's first let's first use the relation between H and AP1. So this is going to be omega P1 AP1 dagger plus AP1 dagger H. Okay, and then we have the AP2 dagger 0 that we shouldn't forget about. Okay, so we've now got 2 terms. We've got AP1 P1 dagger, AP2 dagger on 0 plus AP1 dagger H AP2 dagger 0. So next we simply use the H AP2 dagger commutation relation. Let's keep this first term that we have as it is. And let's do it on the line below. We have enough space, so plus. So now I'm going to keep AP1 dagger on the left and use this commutation relation. It will be omega P2 AP2 dagger plus AP2 dagger H acting on the vacuum. Okay, so the definition is that H on the vacuum state gives 0, so that's going to return 0. So I'm left with just 2 terms. I'm left with omega P1 AP1 dagger AP2 dagger 0 plus omega P2 AP1 dagger AP2 dagger acting on 0. And you can see I can obviously bring together the P1, the omega P1 and the omega P2. And it leaves behind a P1 dagger, a P2 dagger. Okay, so in other words, we have the state that we started with. Okay, so what we find is that the Hamiltonian acting on this state, well, rather the energy of this state, which we get from acting by the Hamiltonian, is simply the sum of omega p1 plus omega p2. Okay, so these separate energies that we would have from p1 and from p2 simply add together. So the interpretation is that a p1 dagger, a p2 dagger 0 is now this state with two particles. Okay, and the energy simply adds. So the energy of particle 1 we would call omega p1. This is p1 squared plus m squared. And omega p2 is p2 squared plus m squared. And obviously we are dealing with one real classical scalar field here. So there's only one m parameter in our theory. So these particles both have the same mass. The only thing that differs between them is the energy and the momentum. So they both have the same mass, this m parameter that entered into our Lagrangian at the start, or our Lagrange density. Okay, so as I said, normally we don't work with simply the states with a daggers and 0. So normally we define it with these energy factors so that we end up with Lorentz invariant states. So normally we would define this two particle state as p1, p2, have a root 2 EP1, we have a factor of root 2 EP2, a P1 dagger, a P2 dagger, 0. So if you wanted to, you could also act with the momentum operator and show that the momenta add together, and you could do all of this stuff. But I don't think we learn very much by doing it, so you've seen it for the Hamiltonian. It'll be a very similar calculation for the momentum. And you could also, in principle, go on to 3 particles or 4 particles or n particles. So it'll be exactly the same manipulations that you do, and the result will be that you have omega 1 plus omega 2 plus omega 3 plus, so dot, 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 for as many particles as you have. So the technique would be the same to calculate that. It's always the case of you just act with these commutation relations, always bringing h to the right. So you keep acting with these states until h hits 0, and then you're done. Okay. So good. So we've seen then that with one field, so with one scalar field, here we can represent 2 particles. We can represent 2 particles, and those 2 particles can have independent energy and momentum. Okay, so now that we're working with multiple particle states, we can now also work out what type of particles we're dealing with here. Let me show you what I mean. Okay, so we have this 2 particle state, which I said we should label, or it's conventional to label P1, P2. Okay, so this is 2EP1, 2EP2, a P1 dagger, a P2 dagger, 0. Okay. But since we know that a P1 dagger, a P2 dagger commute with each other, so now the commutator is 0, we can swap the order of the AP1 and the AP2 terms. Let me kind of figure out where to put that. Let me put that over there. Let me move everything across. It will fit. Okay, so in other words, as I said, we have the same. Well, we could even swap these because these are simply numbers. So why don't we do that? So we can swap everything without changing anything. As in, we haven't picked up any signs, we haven't picked up any additional mathematical factors. Okay, and this we could call, or this would be the state with the labels reversed. So rather than P1, P2, this is the state P2, P1. So in other words, what we're showing here is that the states are symmetric under the exchange of particles. So as I swap P1 and P2, I get the state back. States are symmetric under exchange. So there's a whole class, or there's a special name for these types of particles that are symmetric under exchange. These are known as bosons. Okay, so we're able to show that this quantum theory that we have that followed from this real scalar field Lagrangian is a theory that has bosons in it. Okay, so that's a nice, very simple thing to show. So in principle, we could go even further. We could define an angular momentum operator and show that the spin of these states is going to be 0. So not only are they bosons, but you can show that they're going to be spin 0 bosons, as opposed to spin 1 or spin 2, which could also be bosons. So we could do that. We're not going to do it in this course because of time constraints, but in principle, it's straightforward to do that. That's one interesting further thing that you can do. And another thing that you can sort of start to see from this is that, fermions fermions are going to be particles that are anti-symmetric under exchange. So they must pick up a minus sign under exchange. So you can sort of get a hint of the fact that fermions must be described by, they must have something different that isn't just this commutation relation. Okay, so fermions, the way you quantize them, must be different in some way. And indeed, it turns out that quantizing fermions is slightly different. So one of the differences is that you don't get commutation relations, you get anti-commutation relations. So it's the fact you have anti-commutators that allows you to pick up minus signs that's required so that fermions are anti-symmetric under exchange. But in this theory, where we have commutation relations, they are symmetric, and so they are bosons. Okay, so that then brings us to the end of this lecture. So let me just summarize some of the things that we've done. So the main thing I was trying to get across in this lecture was how particles can emerge from the field pictures. That was the main thing driving our discussion. So along the way, we also noticed a couple of things. So one thing that we had is that we had more practice using commutation relations, so more practice doing calculations in this canonical quantization framework. Another thing we introduced is some notation that you'll see in books and that we'll use later, which is that we describe single particle states often, and I say especially in scattering problems, by momentum eigenstates. Okay, so we label it with the momentum of the particle. So for a single particle momentum eigenstate, we have this square root of 2 times the energy factor, which is a convention that we introduce so that our states are normalized in the Lorentz invariant way, with this factor times the Commutation operator acting on the vacuum. And then the final thing that we were able to show when we looked at the generalization to 2 particles is that we actually have a theory of bosons here, because the states are symmetric under the exchange of particles. Okay, so that pretty much completes our discussion then of the theory of the free real scalar fields. So there's not really much more it's particularly interesting to say. So the next interesting thing we want to do is to add interactions. So rather than simply having free particles that just live and and not do much else, they just live and propagate and that's all they do. We want to introduce interactions between these particles. Okay, so in the next few lectures, we'll discuss how you add these interactions and what the new formalism is, what the new formalism that you need in order to deal with interaction.